Hello friends, myself Dr. Nandakumar Ravali from College of Engineering Ambazugai is going to deal with numerical methods in mechanical engineering. This is our 18th lecture. In previous lecture we have discussed about multiple application of Simpson's 1/3 rule and Simpson's 3/8 rule. So now today we are going to discuss about the introduction to numerical differentiation, then forward difference approximation of first derivative, then backward difference approximation of first derivative, then centered difference approximation of first derivative. Then after that we will go for second derivative, backward difference approximation of second derivative, forward difference approximation of second derivative, and centered difference approximation of second derivative. So now let us see the things. So now generally we used to have one of the dependent parameter and another as a independent parameter. Let us say for example we have the time as a independent parameter and distance s as a dependent parameter. So if a body covers distance s, that is small distance ds, and in small time dt, ds by dt, so rate of change of displacement or position with respect to time gives us velocity. So velocity is a differentiation of distance covered with respect to time. So this is how we are going to define the differentiation. That is nothing but the making small parts of the things and getting the rate of a dependent variable with respect to the independent variable. Now to predict the velocity of parachute, we have used the Taylor series which is expanded. So the Taylor series expanded is expanded. Now say v is the velocity at any time t. So if we want to find out velocity at time t, velocity at time t plus 1, so we know velocity at time t and we want to find out velocity at time t plus 1. So that can be obtained by Taylor series expansion, that is v of suffix t plus 1. So velocity at time ti plus 1 is equal to velocity at time ti plus of v dash first derivative at ti into ti plus of 1 minus of ti, then plus of second derivative v double dash of ti divided by 2 factorial into v of ti plus 1 minus of ti, v of ti, sorry, ti plus 1 time with respect to ti plus 1 into ti square plus of so on plus rn. So these are the remainder terms. So neglecting higher order terms, only first derivative up to first derivative, considering up to first derivative, v of ti plus 1, velocity at time ti plus 1 is equal to velocity at ti plus of v dash ti into ti plus 1 minus of ti, and the remainder terms we call it as a r1. So here we want to find out velocity at time ti, therefore v dash of ti is equal to v of ti plus 1. So this v of ti we transfer on right hand side. So this is v of ti plus 1 minus of v of ti whole divided by, so this term is brought into the denominator, that is ti plus 1 minus of ti minus of r1 divided by ti plus 1 minus of t1. So this is ti, not t1. So first what we did, so this term is on left hand side, so this v of ti is transferred on left hand side, subtracted, and then minus this plus r is transferred on left hand side, then minus r1, then this term which is in multiplication is brought into the denominator. So this is first order approximation. So this first term is first order approximation. First order approximation, we call this as a first order approximation. And this is nothing but the truncation error. So truncation error. Now we'll move towards forward difference approximation of the first derivative. So whatever we obtained v dash, so that is written in terms of function f of x. So first difference approximation of the first derivative, that is given by f dash of xi. So previous formula only, so f of xi plus 1 minus of f of xi whole divided by xi plus 1 minus of xi plus of o into xi plus 1 minus of xi. So this is nothing but h, step size. So this can be written as, so first term is written as this numerator is written as delta f of I divided by, so this denominator xi plus 1 minus of xi is nothing but h, so plus of oh. So where this xi plus 1 minus of xi is nothing but h, step size, whereas delta fi is first forward difference. It is first forward difference, and where h is the step size, that is h is nothing but it is a step size. So now this is about f dash of xi. So when we want to find out first derivative, then that can be obtained by this formula or this first term, and where we neglect this second term, so the second term is neglected, that is called as a truncation error, which introduces a truncation error. So now coming to backward difference derivative of first derivative, backward difference approximation of first derivative, the Taylor series can be expanded in backward to calculate previous value. So forward and backward, say here xi is the term, so forward means one step ahead, that is xi plus 1, and backward means xi minus 1. So in forward difference what we have seen is, so xi plus 1 xi, so from xi we have moved one step ahead, that's why it is called as a forward difference. If we are coming back to f of xi minus 1, then it is called as a backward difference. So now the Taylor series can be expanded in backward to calculate previous value on the basis of present value. So when we know the present value and we want to go in the backward direction on the basis of known value, so this is called as a backward difference. If we are going from xi to xi plus 1, then we call this as a forward difference. So this backward difference formula can be obtained as Taylor series expansion f of xi minus 1 backward, which is equal to f of xi minus of f dash of xi into h plus f double dash of xi h square divided by 2 factorial minus dash 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 plus and so on f to the power of n xi h to the power of n divided by n factorial. So after this, what we do, the higher terms are neglected, truncated, and only the first order derivative is taken. So therefore what we do is this f dash of xi is equal to, so this is brought on left hand side and this is brought on right hand side. So when we transfer this on right hand side, that is f of xi minus of f of xi minus 1 divided by h. So this h is transferred, so this complete term, if we transfer on left hand side and this term on right hand side, then we get this plus of the higher order terms we call as r1. So neglecting this as a truncation error, so we can write as f dash of xi is equal to delta del of f of I divided by h. So this is the derivative obtained by backward difference. So in backward difference we go one step in backward direction, in forward difference we go one step ahead of the existing term, that is xi. So xi plus 1, that then we call it as a forward difference. If xi to xi minus 1, then we call it as a backward difference. So this is called as a first backward difference, that is delta fi is known as first backward difference, is known as first backward difference. It is known as first backward difference. So now coming to centered difference approximation. Centered difference approximation of first derivative. So we know both forward difference and backward difference. So we write backward difference, forward difference. So this is backward, forward. This must be centered difference. This must be centered difference. Centered difference approximation. So in this centered difference approximation, what we do, first we write forward difference formula for Taylor series, that is f of xi plus 1 is equal to f of xi plus of f dash of xi into h plus of f double dash of xi h square divided by 2 factorial and plus so on. So this is equation number 1, say. So this is according to forward difference approximation of first derivative. So this is first derivative, not second, first derivative, first derivative. Then again we go for backward difference formula, Taylor series expansion, f of xi minus 1 is equal to f of xi plus of f dash, sorry, minus of f dash of xi h plus of f double dash of xi h square divided by 2 factorial minus and so on. So this we call as equation number 2. So now here Subtracting equation 2 from 1. Subtracting equation 2 from equation 1, we get. So here we change the signs. So second equation minus, minus, minus becomes plus, plus becomes minus, and so on. So first term f of xi plus 1 minus of f of xi minus 1, which is equal to f of xi. F of xi gets cancelled. So f dash of xi plus of f dash of xih. So 2 times f dash of xih plus 2 times f double dash of xi h square divided by 2 factorial, and so on. So this we call as equation number 3. So what we want to do, we want to find out derivative, differentiation, and neglecting these higher terms. So what we can do is, first we transfer this term f double dash and on a right hand side. So this term gets cancelled. So f triple dash of x to the power of 3 factorial is going to be added here. So this term is transferred on left hand side, and this term is transferred on right hand side. Then we get this as f dash of xi is equal to, so this term if we transfer on right hand side, so this becomes negative minus 2 into h, which is equal to minus of f of xi plus 1 minus minus plus f of, or we write this as minus, and then we take this bracket f of xi minus 1. So this term is transferred on right hand side. Then plus of 2 times, that is 2 times f triple dash of xi h to the power of 3 divided by 3 factorial. So again multiplying both side by minus, so and then dividing by minus 1 by 2, dividing by minus 1 by 2 on both side. So we get dividing by minus 2 on both side, we get, so this as f dash of xi dividing by minus 2h. So minus 2h gets cancelled. So f dash of xi is going to be there on left hand side, and minus minus plus, so we get this as f of xi plus 1 minus f of xi minus 1 divided by 2h. Then minus divided by minus means this plus becomes minus, minus 2 gets cancelled. So f triple dash of xi h to the power of 3 divided by h into 3 factorial. 3 factorial means 6. So h gets cancelled, so h square is going to remain. So this can be written like this: f dash of xi is equal to f of xi plus 1 minus f of xi minus 1 divided by 2h minus of, so this term, complete term, is called as OH square. So this is the truncation error. So this we call as equation number 4, gives us center difference approximation of first derivative. Center difference approximation of first derivative. Now moving to next thing, that is second derivative. So again here there is a mistake. So now we go for forward difference. So this is not backward difference, it is forward difference. Forward difference approximation of second derivative. So forward difference approximation of second derivative is given by f double dash of xi second derivative, which is equal to f of xi plus 2 minus of 2 f of xi plus 1 plus of f of xi divided by h square, where h is the step size, plus of oh. This is the truncation error. So this is known as forward difference approximation of second derivative. Then coming to backward difference. Backward difference approximation of second derivative, which is given by f double dash of xi. Forward difference means xi plus 1, xi plus 2. So it starts at xi, then xi plus 1 and xi plus 2. So this is called as a forward difference. So now backward difference formula we write here, f double dash of xi, that is f of xi minus 2f of xi minus 1 plus of f of xi minus 2 whole divided by h square plus of oh. So this is backward difference approximation of second derivative. Then centered difference approximation of second derivative is given by f double dash of xi. So here it is backward difference in the sense xi minus 1, xi minus 2. So it is taken in reverse way. So xi minus 1, xi minus 2. So it was xi plus 1, xi plus 2, which was called as a forward difference, center difference. So here, which is equal to f of xi plus 1 minus 2 f of xi plus of f of xi minus 1 whole divided by h square plus of oh square. So this is everywhere h square must be there, h square. Okay, so this is called as a truncation error. So this formula, say formula number 5, equation number 5, equation number 6 and equation number 7 give us the forward difference approximation of second derivative. Now let us start with certain numericals which will help us to understand. So this numerical differentiation. So let us consider one numerical. With the help of numerical, we'll find the first derivative. So question is like this: use forward forward, comma backward, and center difference approximation. To estimate first derivative of so function f of x is given. F of x is equal to minus 0.1 x to the power of 4 minus 0.15 x to the power of 3 minus 0.5 x square minus 0.25x plus 1.2. So this derivative has to be obtained at the value of x is equal to 0.5 using step size of h is equal to 0.5 and h is equal to 0.25. so that is nothing but once we have to take h is equal to 0.5, so that will become first problem, then second problem by taking h is equal to 0.25. so this problem has to be solved twice. So once we have to take h is equal to 0.5 and once we have to take h is equal to 0.25. so now let us see the direct derivative which is computed. So direct solution, what will be the exact derivative? Direct derivative is computed, or direct derivative. So first we differentiate this f of x. So that is f dash of x, which is equal to minus 0.4 x to the power of 3. So derivative of this minus 0.1 x to the power of 4 is minus 0.4 x to the power of 3 minus 0.15 into 3 that is 0.45 x square, then this 0.5 x square, that is minus 1.0 x minus 0.25. so differentiation of this given equation 1 is this one. So at 0.5, so f dash of 0.5, so if we substitute 0.5 in place of x, that is minus 0.4 into 0.5 to the power of 3 minus 0.45 into 0.5 to the power of 2 minus 1 into 0.5 minus 0.25. so this derivative, if we obtain, this will be minus 0.9125. so first derivative at 0.5 for this given function f of x is minus 0.9125. this is called as a true derivative. So this is true derivative which we have obtained by differentiating function f of x. So now actually he has asked us to find out the numerical differentiation taking h is equal to 0.5 and h is equal to 0.25. so first we take h is equal to 0.5. so for h is equal to 0.5 for h is equal to 0.5, so if h is equal to 0.5 is there and we want to find out the differentiation at 0.5, so xi, if we take xi as 0.5, then backward difference, if we move one step behind it, that is xi minus 1, so step size is 0.5. 0.5 minus of 0.5 means 0, and xi plus 1, if we go one step ahead, so 0.5 plus 0.5, that is 1.0. so if we find out function f of x I minus 1. Xi minus 1 means in place of x, so function is f of x is equal to, which is given in this problem, is minus 0.1 x to the power of 4 minus 0.15 x to the power of 3 minus 0.5 x square minus 0.25 x plus 1.2. So everywhere, wherever there is x in this, so if we substitute 0, so this 0, this 0, this 0, this 0, then the function value is going to become 1.2. So f of xi value in place of x, if we substitute 0.5 everywhere here, 0.5 in this equation, then f of xi at 0.5 we get as 0.925, then it becomes 0.925. So when we substitute x is equal to 0.5 everywhere in this above equation, so then we get this equation as 0.925. And after that, f of xi plus 1, so if we substitute x is equal to 1 in this given equation, then function becomes 0.2. So therefore now we want to use forward difference, backward difference, and center difference. So if we want to use forward difference, divided difference, forward divided difference formula. So forward divided difference formula is f dash of xi, which is given by f of xi plus 1 minus of f of xi divided by h. So if we substitute here, f of xi plus 1, f of xi plus 1 is 0.2 minus of f of xi is 0.925, 0.925 divided by h value is 0.5. So then we get this as minus 1.45 as the derivative. So true derivative which we obtained, f dash of 0.5 in previous case, here first derivative which we obtained is minus 0.9125 minus 0.9125 minus 0.9125. So this is the exact answer. True answer is this. So but what we obtained here is 1 minus 1.45. So the true error, relative true error, if we want to find out, so true value is minus 0.9125 minus of minus plus. So this value which we obtained is 1.45 whole divided by minus 0.9125. So true value minus approximate value divided by true value into 100. So then this is going to be minus 58.9%. So here error is 58.9%. So this is the differentiation which we obtained by forward divided difference. So now we again obtain this by backward divided difference formula. Backward divided difference. So f dash of xi is equal to f of xi minus f of xi minus 1 divided by h. So here f of xi is 0.925 minus f of xi minus 1 is 1.2. 1.2 divided by h value is 0.5. So if we obtain this, this is going to be minus 0.55. So this is the differentiation at 0.5, first derivative. So true error can be obtained. So true value is minus 0.9125 0.25 minus of minus, so this approximate value is 0.55. So 0.55 divided by true value is minus 0.9125 into 100. So this error we get as 39.7%. so here error is less, so 39.7%. Then again we go for center divided difference formula. So using center divided difference formula. So center divided difference is given by f dash of xi is equal to f of xi plus 1 minus f of xi minus 1 divided by h, or 2h. So this is 2h divided by 2h. So if we see this formula, center divided difference, so there is 2h in the denominator, so 2h is taken. So here this is equal to f of xi plus 1 is 0.2 minus of f of xi minus 1 is 1.2 divided by 2h. 2 into h is 0.5. So this works out to be minus 1.0. So true error, true value is 0.9125 minus of minus 1 is plus 1 divided by minus 0.9125 into 100. So this works out as minus 0.96, minus 0.9.6 as the true error. So here we can see here center divided difference formula gives us minimum error. Now this is solved using step size h is equal to 0.5. So higher is the step size, lower will be the accuracy, and lower is the step size h, then it will give higher accuracy. So here we have taken h size, step size as 0.5. Now same problem we want to solve by taking step size h is equal to 0.25. So now we can see here, so function f of x, which is given as f of x is equal to minus 0.1 x to the power of 4 minus 0.15 x to the power of 3 minus 0.5 x square minus 0.25 x plus 1.2. So taking h is equal to step size 0.25. So let us consider xi is equal to 0.5. So we want to find out the differentiation at x is equal to 0.5. So we take here xi is equal to 0.5 and xi plus 1 means 0.5 plus of step size is 0.25, that is 0.75, and xi minus 1 means 0.25 minus of 0.5 minus of 0.25, so this becomes 0.25. So initially we start with 0.5, so subtracting 0.25 from 0.5 is 0.25, adding 0.25 to 5 is 0.75, so plus 1 minus 1. So now f of xi minus 1 function value, so if we substitute 0.25 in this given equation, then in place of x, if we substitute 0.25, then we get it as 1.1035156. So if we substitute 0.5, then that becomes f of xi, which is equal to 0.925. And if we substitute x value as 0.75, then f of xi plus 1. So this becomes 0.6363, 0.63632813. So now again we use forward difference, backward difference, and center divided difference formula. So forward difference formula, forward divided difference formula, f dash of xi is equal to f of xi plus 1 minus of f of xi divided by h. So f of xi plus 1 value is 0.6363, 0.63632813 minus of f of xi is 0.925 divided by h value. H value is step size is 0.25. So then this becomes minus 1.155. Then true error, if we want to find out, so true value which was obtained is minus 0.9125, minus true value f dash of x is minus 0.9125. so true value is minus 0.9125 minus of this approximate value, minus of minus, it becomes plus 1.155 divided by true value is again minus 0.9125 into 100. So this true error works out to be minus 26%, minus 26.5%. So if we compare this with the earlier, so it was 58.9%. So when we use the higher step size, error was larger. Now here error is only 26%, it is 50% of previous. So then backward difference, if we take backward divided difference, then f dash of xi is equal to f of xi minus of f of xi minus 1 divided by h. So f of xi value is 0.925 minus of 1.1035156 divided by, so h value is 0.25. So this is going to be minus 0.714. So this is approximate derivative using backward divided difference. So true error is given by minus 0.9125. So minus 0.9125 is the exact derivative. Then minus of minus plus point. So this is approximate derivative which we obtained by using numerical method, that is 7.714 divided by true value, that is minus 0.9125 into 100. So which is going to be 21.7%. This is going to be 21.7%. So in previous case this error was 39.7%. when we took the step size h is equal to 0.5, so error was 39.7%. now here error is 21.7% using backward divided difference formula. Now we use center divided difference formula. Center divided difference formula. F dash of xi is equal to f of xi plus 1 minus f of xi minus 1 divided by 2h, which is equal to f of xi plus 1 is 0.63 2813 minus xi minus 1 is minus 1.1035156 divided by 2 into h is 0.25. So this works out to be minus 0.934. So minus 0.934 is the answer. Derivative which we obtained from center divided difference formula. So true error if we want to find out. So true error is again minus 0.9125 minus of minus plus, that is 0.934 divided by true value is minus 0.9125 into 100. So this error is going to minus 2.4%. So if we compare this with the previous error, so it was minus 9.6%. So now this error has reduced to minus 0.247. So this is the minimum error. So comparing with other methods, that is forward divided difference, backward divided difference, center divided difference, so the error in center divided difference is minimum, and when we take a lower step size, the error is going to get reduced than the previous values, or higher step size. If lower is the step size, lower will be the error, and that too the error which we have seen using center divided difference formula is less. So now I will stop here, and in next class we will discuss about the second derivative as well as some other numericals to find out the derivative of transcendental functions or trigonometric functions. So today we stop here, and next class we will discuss.